Hi, my name is Sandra Palau, and this is a joint work with Natalia Cardona. We work with Galton Watson's processes in varying environment. These are branching processes where all the individuals in the same generation have the same offspring distribution, but this distribution vary among generations. We are going to denote by Qn the distributions of the individuals in the n-1 generation. By using the branching property, we can see that the generating function of the population size at time n is equal to the composition of F1 with F2 up to Fn of S, where Fi is the generating function associated with Qi. If we differentiate, we can obtain that the mean value of set n is equal to the product of the mean values of the Fi up to F1 up to Fn, and we have something similar with the second moment. It will be in terms of the first and the second derivative of the Fi's. We wanted to work with the critical case. This is the case where the previous series goes to infinity, but also the product of mu n with the partial sum. If we define an as that product over 2, we can prove that set n over an conditional on survival converge in distribution to a standard exponential random variable. With Natalia, what we did was to prove this in a probability approach. And what we used was a characterization using g of x g-size Bayes transform that are defined as here. Actually, what we use is that an exponential random variable is characterized by this equation where y double dot is the y squared transform of y, and y dot prime are y transform of y, and u is a uniform random variable, everything independent. And actually, this is not the only characterization that we can obtain with size Bayes transformations. We can see that xn conditional on survival converge to a variable y if and only if xn dot converge in distribution to y dot, where here I am working with the y transformation. And in this case, it is also true that xn double dot converge to y double dot, where these are the y squared transformations of y and xn. So in our case, set n dot, it is the number of individuals at the generation n in a Galton Watson tree with a marked genealogical line, like this one, that I'm going to call it spine. How do we construct the tree? Well, we start with a marked particle, and any marked particle at generation m will give birth accordingly as q dot m plus 1. From all the children, we select 1 as the next new marked particle, and any unmarked particle will give birth accordingly as qm plus 1 if it is at generation m. What it is set double dot? Well, it is the number of individuals at generation m in a Galton Watson tree with 2 marked genealogical lines. So we need to say when the second spine it is created. We are going to assume that it has that distribution. So any particle that is not that special one will behave as before, and this one will give birth accordingly as q double dot, that it is the q minus 1 transformation of qr plus 1, and from all the children we are going to select 2. Then we will have something as in this picture, and if we want to say how many individuals I have at generation n in a tree with 2 spines, we can decompose it as how many individuals I have attached to the longer span plus how many individuals are attached to the shorter span, that it is something like this. And observe that here, the shorter span, the environment is changing. We start at generation Kn+1, and we only move n minus Kn+1 generation. Then, if we assume that set n over an conditional on survival converge in distribution to a variable y that we don't know what it is, we will see by the characterization that set double dot will converge to the y dot, and set dot over an converge to y dot. Here, we need to do the correct scaling. And after that, the last one will converge to y dot prime. Therefore, with Natalia, what we show is that the extra term that we have here converges to a uniform random variable. And this means that y has to be an exponential random variable. Thank you so much.